This one is our working group.
That's what it was.
Goddard is only Goddard.
I do.
Okay. Good afternoon, everyone. So we are happy to have Dr. Sanchita Pal with us. She did her PhD from ISA Kolkata in 2020. After that, she moved to University of Helsinki, and she worked there for about 2 years. And recently, she has joined NASA Goddard. So her research interest lies in understanding the solar atmosphere, particularly space weather aspects of solar physics. And today she will be talking about the flux slopes and the heliosphere, their evolution and identification. So over to you, Sanchita.
Thank you. Okay, so good afternoon. My talk's title is flux slopes in the heliosphere, their evolution and identification. So first of all, I will So I'll first just introduce myself, what I do there in NASA's HSD, HSD's Heliospheric Science Division's NASA's group. So we are engaged with a group that is called Large Scale Structures Origination from the Sun, the group's name, working group's name, LASO. So what we do fundamental science, we start the community and also please the research to operation group, because the moon to Mars, these kind of operation, they take help from us to identify the energetic phenomena from sun and how they can take care of their instruments from these kind of events. So we do different kind of things. We do theory modeling and we do case event analysis and then observation, artificial intelligence, and also we create synergies between research and operations. So my expertise there is mainly on case event analysis and artificial intelligence, and also I'm engaged with this group, the observation tools. So as we know that our heliosphere, which is a curvature created by the sun and its planets. So this is filled with solar wind. So that is a continuous propagation of solar magnetized plasma from the sun towards the heliosphere. And so sometimes what happens, very often it is seen that the huge eruptions of magnetized plasma occur, and those kind of things are identified as coronal mass ejections. And these events are very energetic, and also they have a high speed. Sometimes they have high speed.
Can I ask a question?
Yeah.
In the previous image, so the left one, is it? From where this observation is taken?
This is UTIPS.
Yeah.
It is UT.
Yeah.
Okay. And this is what you have, what it is showing is the CME plasma going outward, or it's just a high stream solar wind, or what?
This is the solar wind. So here it is overlap of this. So this is mainly the plasma
Density.
Yeah, density.
Yeah,
So they have both.
Okay.
Mainly the color shows the density.
Yeah. So I was wondering whether this event is a CME or just.
Yeah, it might be. I mean, just this one. Okay. So the solar magnetic storm, which is I just told, that is the CME. So there are several different kind of series observed in remote observation. I mean in white light observation. So those are kind of flux slopes, loops, jet, failed, and outflow. So flux slopes which have put this kind of view in the coronal graph, observe this kind of phenomena which occur the main solar body, the sun disk, and then only we can see this structure in the faint corona. So this is the flux loop structure when we can see the three structure like leading is the cavity where the flux loop resides, and then the core. And then next is the loop structure where we sometimes lose the cavity or core, but the loop structure is observed. I mean the leading edge structure. And then the jet CMEs, which sometimes people say that this is not a CME, this is just a jet, so which has a less than 40 degree of angular V. And then the failed CME, which sometimes appear in the C2, like very near to the sun, but sometimes that does not appear in the C3 coronagraph, that is higher distance from the sun. And then outflow, which does not look like jet, which does not have a loop or cavity structure, it's just kind of a big eruption, which is not that much well configured. So CMEs are majorly associated with active regions. So active regions are the regions on the sun, which we can see using a telescope and proper filter. We can see the sunspots. And this is a magnetogram where you can see the red, the black and white patches, which is the negative and positive magnetic field region on the sun. So these kind of regions, if they are very much energetic, then excess magnetic energy, they erupt in the form of the solar eruption. So here the zoom in version has been shown here. So this is one type of source of this kind of event, but not only from this active region the eruption occurs, it also can form at the higher height from the sun. So I will talk about this in my next slide, later. So once the CME launched in the interplanetary medium, then they can be probed in situ by this spacecraft, where it is, so it is an example of stereo spacecraft, which is just sitting here, and you can see that the structure is so big, the series structure, so it cannot be probed whole. So that's why we mainly probe on the locally, and we do analysis of the local structures, and then we try to get a view of the global structure. So this is the procedure of in situ observation of this kind of large scale structure events. And then, as you can see here, so this is a schematic of the CME, which is drawn based on the observation, and this red line shows the spacecraft propagation through the schematic CME. And we get mainly this observation at this point, so we don't get this. So if depending on the spacecraft's position, the observation of the flux flow can vary, but their intrinsic properties should not change much. Once they launch in the interplanetary medium, they mainly appear as flux slopes, but they result shock and seep region. So shock appears because of their speed difference between the CME and the interplanetary medium. And then the sheep region is mainly the heliosphere, which is accumulated in front of the CME because it is propagating and dragging all the elements in front of it. So this sheep region you can see here. And in the cartoon, it is like this region, the turbulent sheep region I just mentioned, and then the flux slope region. So this flux slope has been observed from several years, and they are mainly categorized based on their properties like enhanced magnetic field strength, then smooth rotating magnetic vectors, low proton temperature as it's a magnetized region. I mean, magnetic field is very intense there, and low plasma. So here, this is the magnetic cloud region, means the series flux slope region. So inside the CME, the magnetic field is inside the CME flux. So the magnetic field is twisted in nature, and this we can see even in the observation also, that you can see the field lines here. The BXYZ, that is the vector component of the field, and it has a very nice rotation here. So this rotation proves that they exist in twisted in nature, and this magnetic field components are mainly not only the magnetic field components along with the speed. So they are mainly the geoaffective nature of the CME. So once the CME launched in the heliosphere, if they have a magnetic field which is which can create which can reconnect with the Earth's magnetic field, which is north to south, which is south to north, and so if the magnetic field is north to south, then it should reconnect. And once it reconnects, it enters the energetic particle in the Earth's atmosphere through this polar region, which we can see through this aurora. And also it inserts the energetic particle, which enhance the ring current, and by that the magnetic field of the Earth, it gets disrupted, and thus the geomagnetic storm occurs. So the energy transfer from the solar storm to the magnetosphere can be expressed in this through this equation, where the V is the speed and the magnetic field intensity, and the theta is the angle between dy and dz. So it means that well, it depends, the CMEs geoeffectiveness depends on the velocity as well as magnetic field intensity and the angle between their orientation. So these are the energy source in the in the Earth's atmosphere. But
What is L naught?
it's okay. L naught is the distance between the it is actually 6 RE, so 6 solar areas. So it's the distance between Earth's magnetosphere and this Borshock region.
So it is fixed.
It is fixed. Yeah, I mean there are many several studies which say that it's not 6, it's not 6, it's 7, it's 5, but it is around that and it is constant.
It is dependent on Earth's magnetic field only. That's
Yeah.
what I'm saying. He is a magnetic field.
No, it's a CMEs. Yeah,
It's a flux rope magnetic.
flux ropes. D and D both are of flux ropes. I mean, CMEs. So
Yeah, no, I just was just thinking. I mean, I understand energy transfer depends on B, but why on the velocity of this?
okay. So this is mainly the Poynting flux. So equal to
okay.
V cross B. So yeah, there is some. Because this is the energy, electromagnetic energy inside into the flux. So these are the energy source and the energy sinks are mainly the ring current particle injection. So via that they lose their energy, the particles, and then auroral particle injection and then Joule dissipation in the ionosphere and atmospheric heating. So these are very broad topics. I don't study on these things. So these are just I have put it here so to make you understand that how these CMEs can impact the Earth's atmosphere and things. So here is the QR code of my thesis. If you are interested, how the CME geoeffectiveness occur and how they are influencing the Earth's biosphere. These are things I did in my PhD study. So you can go and see more details. And so once this energetic, once this geomagnetic storms occur, so they are very harmful for the telecommunication and then the GPS system, even the astronauts' health. So that's why we need to probe the CME so that we can get to know that whether the CME is geoeffective or not. And if it is geoeffective, so that the instruments can take measures to save those. So first I will a bit say about the flux rope identification.
When you
So
say whether it's effective or not,
Yeah,
you have some critical number over which you
Uh,
say that this is what we have to worry about.
yeah, so there are two things. One is the duration of the CME, I mean the magnetic field DC, and one is the intensity. So if the duration is like more than 3 hours and the intensity is more than -10 nanometer, so then it is the study says that this is the
So it means, some parameters which is of, changing in the earth, whether it is a TST index change, duration or something, that
Yeah.
is what is.
yeah. TST index depends on this duration and magnetic index. Yes, yes.
So basically, I mean, if you can put a cutoff on this epsilon here, right? So if your epsilon is greater than a particular value,
Yes.
then of course it will be a geoeffective because there's the energy transfer rate from stone to
Yeah,
magnetosphere.
yeah.
Basically.
But the
Yeah.
direction is also important. So just.
But that is taken care of.
That is why.
Theta is.
Yeah. So what I'm saying is if epsilon is greater than a particular value, then you can say that, okay, yeah, this is.
This will be there.
That's so epsilon is a very good parameter to detect whether that's in. So why flux rope identification is needed? Because as I said that we keep on the spacecraft which are there in the heliosphere, they keep on detecting the solar wind. And whenever there is smooth rotation, then they detect that this is a sea. I mean, this is a flux. And whenever there is no smooth rotation or no magnetic field change, like abrupt magnetic field change, then it is said that there is no kind of transient events exist. So then we don't have to worry. So that's why this is important to identify flux rope. So here I have shown one picture, which actually shows the CME flux rope crossing between this dashed line. I'm sorry, it's not very great. So between this dashed line, you can see the magnetic field has very smooth rotation, and this thing can be easily understood by the picture. So that is the image. So that image means this is the image. This is called photographs, which are created based on the magnetic field component. So they in the plane of YC plane and then XC plane and then YX plane. So that you can see the big rotation. This you can only see when there is a flux flow. And then next I will show. See here is here is a CME ejector crossing. So what does ejector mean? When there is no flux flow, but CME exists. When it happens, when the spacecraft cross through the CME's leg, or sometimes it does not cross through the CME's flux flow at all, it's just crossing through the sheath region, then this kind of thing you can observe. There, you can see here the magnetic field intensity increased. Few signatures are similar to the CMEs, but see magnetic field the orientation is not at all. It does not have a smooth orientation. It is smooth, but not like positive to negative, like here you can see, not like that. So then these kind of things will show in the holograms. They don't show much of any sense. It does not make much sense. And then another thing,
You also see some fluctuation, quasi-periodicity. What is that?
Here,
In the top panel, in the B nanotesla.
here,
See
this
between,
level,
even the top panel. You have
periodicity here. Oh, okay. So this kind of periodicity you will see in the sheath region, because these are not the series proper. That the heliospheric.
So sheets are multi-layer.
Sometimes it happens.
I think it's a turbulent plasma, so you
Yes.
will have a cluster of.
So
magnetic
that's what it is, showing some special structure.
Uh-huh.
That's what, I think it's a turbulent plasma there.
So that sectional area size distribution, you can probably estimate from there, the thickness of that.
The sheath.
I think many people,
Yes, it's a good thing to start with. How this. Prevails. Yeah, and next is this, the rightmost panel, that is the solar wind having no flux flow. So you cannot see any rotation, nothing is here. So we can, so here the idea is if we use, so the idea is if we use the automatic identification criteria where we can detect the smooth rotation or the not, whether there is no rotation, this kind of thing, then we can use that in identifying C or flux flow in the in situ observation. So for doing this
Let
automatic,
me ask you, there's probably it's a preview though. So in terms of the geo-effectiveness, is there any difference between the ejector scenario and the flux flow scenario?
sometimes, because for the ejector, mostly no, but sometimes what happens, if the ejector has a continuous negative DC, I mean, if you can see here in this picture, so here DC is a positive continuously, right? So it is not at all opposite. But if it has a structure which is continuous negative DC, then we have to worry about this. So this is a very important thing that we have to classify the CME flux flow as well as this one, as well as this one. These are also important. We cannot say that these are normal flux flow. They also should be classified.
so solar wind with no flux scope is like you have like features which are not rotating as well as it's like simple fluctuations.
Simple Yeah, and also you can see sometimes SIR, stream interaction regions, that we are not interested. I mean, we are not. So.
Yeah, but the problem is, people have to look at the scale also, because your D here, it's much smaller range, so it's actually flat.
Yeah.
It shows fluctuation.
Yeah.
So that's a diagram fluctuation of the solar wind, not really.
Yeah, it could be well.
It is plotted only between 0 to 6 or something.
Yes, that one, yeah, that particular, yeah. So, so for this automatic detection, we need a huge amount of data, and that is the problem, because till now, whatever flux flows has been observed with the wind era and the recent flux flow, that does not, that is not more than 500. So it's like 400 something. So that's not enough for doing automatic identification. So that's why what we do synthetic flux flow. We generate synthetic flux flow based on the CME structure. So you can see here, this one. So this is a CME flux flow, the portion of the CME flux flow, which is interacting the spacecraft. So this can be modeled using the existing, like this can be modeled with physics-based analytical model. And those models include several kind of models, like, I'll tell that. Then this you can see here. So this is actually model structure. The blue, this model is not that good, but sometimes it behaves very well. And you can see, although it is not in the time series, although it is not performing well, but in the image structure, it is not that different from the real observation. Real observation is the pink, and the sky blue is the simulated. So this thing has been used, this approach, the previous studies, and they got success, but not 100%. Of course, it cannot be, because it is a simulated thing.
So,
And then-
so what they are trying to do here, they have the rear observation and they assume a flux of model.
Mhm.
And they
And
locate it,
fit that.
and yeah, and they know the location of the spacecraft, location of the sun, and then they try to adjust the flux of in such a manner that it tries to match with the.
Yeah, and that will be automatically, I mean.
Yeah, I know,
Yeah.
and then they will try to minimize the.
Minimize the difference, and then we get this. Yeah. And then for the non-flux stroke case, we do this thing, we do pull the time series from Gaussian distribution, and that is that
But
just.
let me understand, to generate these holograms also, you need, or is there any restrictions on if there's a very fast CME,
Yeah, yeah.
passes by very quickly? Can you generate, of course, for the instrument data, probably you have enough cadence.
Yes. it
So the
has-
cadence is good enough
Yeah,
to capture.
yeah. So yeah, so thus we can create synthetic flux stroke and non-flux stroke data. And then this is the procedure of their identification. I will not go much here because this is my very new project which I started. Even I am not also that much expert in this. So our group does it. So we train data, we use train data from these photograms, mainly from model flux stroke and model non-flux stroke. Then we use the PCNN, that is the convolutional neural network. And that is, the structure is like this. So what it does, it uses kernels and then the pictures which it generated, the hologram pictures. So the convolution operation is done with the kernels. And then finally, from the pictures, like the three pictures which I showed, and then they can be illustrated in the huge series of the properties. And then from there, it can easily detected whether it is like flux stroke or non-flux. And then for the validation, we use the wind ICME catalog, which is an existing catalog, which catalogs the CMEs based on their properties, and there are like 400 CMEs there. And using that, we validate the CMEs. And then, so this part has been done, and even it is published in this paper. You can, if you are interested, you can go. And then what I am doing, so this is this part. So whether the CME is crossed through, whether the spacecraft is crossed through its apex. So apex means the nose, means where you can see very good nature of the very good magnetic field orientation of the CME, and then the plane crossing. So plane crossing is when the CME is, when the spacecraft is crossing through the leg, when you will not see the wood rotation. So so based on the simulated flux strokes properties, you can get many simulated flux strokes of this apex crossing and plane crossing. And then you can use that in the model, in the AI model. Yeah, so here you can see this is a flux stroke and flux stroke of the CV, and this is the spacecraft. This is the part where the apex is the spacecraft is crossing through the apex, and this is where it is crossing through the leg. So we can, using this procedure, we can classify the CME's flux stroke, even the flux stroke, whether the flux stroke is crossed through apex or through the legs, and whether there is not at all any flux stroke. So this will be very useful for the upcoming India's mission Sanchita Pal's magnetometer data, which it will generate the PHP while it will give us, and then we can directly view. It will actually lessen our, it will our effort of manually identify the flux, so that will be bit easy. Of course, yeah.
All these cities immediately assume that you have a single flux.
Yes, of course. Yeah, if there are
And I think you
multiple
are aware there were new results coming from
complex.
solar orbiter also, that there are possibilities of multiple fluxes.
Yeah.
Then you have to, your entire exercise will be
More
I mean,
complex,
more complex.
more complex. Yes.
So I have a question on similar lines. I mean, when you say that you are using machine learning to distinguish between these two scenarios, the apex crossing and plane crossing,
Yeah.
and you're using neural network, so first you have to have some training data set.
Yeah.
So in the training data set, you need to have some real scenarios where you can distinguish between the apex crossing and the plane crossing. How did you do that?
Oh, okay. So that this angle you see, the beta and lambda angle, the lambda and I angle, so they mainly help in that. So once you feed the CME with the cylindrical flux stroke or any flux stroke model, then you will get theta and phi. Then from
So
theta
you
and
have
phi-
already observed data enough, where I mean, like GCS model fitted something, if you have already some catalog, you have some catalog already.
We have some catalog, but it does not depend on the catalog. It does depend on each event by event.
Yeah,
analysis.
so that has to be trained. I mean, that's his point, huh?
So we get the theta and phi from each model feed, and then from theta phi, we have equation that we can convert in I and theta. And then we have previous studies, yeah, here the catalog counts. We have previous catalog studies where the beta and I has certain value when we will see that it is apex crossing or not. Then,
So existing table has to be there. So-
yeah, it is there. It is there. So this is the, yeah, so next I'll go to the next part, that is the evolution. So forecasting CME's magnetic field is very necessary as it gives us the geoeffectiveness of the CME's geoeffective prediction. So here, there are several models which, several methods which are doing this thing. So there are, of course, 3D diagram models, which is like Euphoria and then a new model, and there are also the models from the Michigan group, who does this simulation of the heliosphere, and they insert a CME on a certain solar or a certain distance from the sun, and then they propagate itself similarly, and then they get the CME's magnetic nature, magnetic characteristics, as well as the plasma characteristics, as is shown here. But the thing is, it is computationally expensive. But the good point is they give us along with magnetic field, they give us the plasma properties also. But as it is computationally expensive, and as we have only kind of 3 to 4 or 2 to 5 days to predict the CMEs once it erupts, so that's why better we can shift to the semi-analytical or analytical model. So there are many models which are already been established. So these are the models, and these models can do predict the CMEs magnetic field. But the thing is that they cannot predict the duration of the CME, which is also important. So the, our model, which we very recently developed, that is a CMCP model, and there we showed how we can even predict the duration of the CME as well as the magnetic field characteristics. So here, we generally for this,
Can you say a little more about that model ingredient?
yeah,
It's a
yeah.
semi-analytical or
Yeah,
parametric, what all parameters?
here.
Oh, you're coming back.
Yeah. So the general approach for this kind of prediction is first we get the near sun CME observation, and we constant the CME at around 15 RS, and then we input the CME to the database, and then the database model will proceed the CME with self-expansion, self-similar expansion, and then we assume the CME following flux flow.
So is this drag-based model, is it very similar to what Prasad said?
Yeah. It's a
Or
same.
The
yeah,
proportionality
yeah.
and all that, and you
Yeah.
also use cylinder geometry. and all that?
Yeah. So we can use this all kind of structures, linear force tree model, circular model, then non-linear model. So I have used in my paper, I have used the linear force tree model. This is the simple model, but linear force tree model with expansion, because the CME expands while we propagate. So we constrain the CME at the near sun region. Then at this block, we fit this input to the model, and then we let the model propagate in the interplanetary medium with expansion. And then once it reach at any observational point, then we validate our result with the existing spacecraft. So the recently launched satellite, which are PSP and solar orbiter, will be used in the near sun this block, near sun CME observation, as well as in this block where the CME evolution will be also as an input to the model. So here I have shown the one result from this model. So that is, this is the sun solar disk, and this structure, cylindrical structure, is actually the structure of the CME, not the whole CME. That is the structure where the which is expected to reach at Earth. So this, whatever the field line orientation and whatever steel, everything we got from the real observation near the sun. And once we get this thing, we put it in the MCP model, and then this gives us this red line that is the predicted.
Yes,
So-
there was one thing, sorry, maybe I missed it. So you are assuming it to be this is spiral structure in a cylindrical shape, right?
It's,
This
yeah,
is what you are assuming. And when you are applying the drag-based model, you assume this shape to be like this, propagating into the heliosphere.
we,
So you are not, okay, so you are not considering the entire CME
no, only the,
surface area for compute, because that's what the Prasad does. He
Involved,
they
yeah.
use the GPS, and they assume that one half of the sphere is in contact with the solar wind. But here you are assuming only this cylinder,
Yeah.
this empirical cylinder is something that is propagating into the medium. And so you get the drag based on the surface area of this.
Yes, only on this, yeah.
And this cylinder is continuously expanding
Yeah,
using self-cylinder. So my question here is, okay, I mean, this could be easy to do, but here you are not assuming, you are not taking into some flux rope type structure. Because this is a very simple cylindrical,
cylindrical structure, but flux rope, which is, say if the flux rope is like big and we are taking on this portion of the local observing portion, not the global thing. Because the spacecraft.
so with this, you will only be able to understand the apex of the CME, the magnetic evolution at the apex.
Interaction one.
Interaction with the satellite.
No, the satellite interaction can happen even at the legs.
Yeah,
So
But I'm
that
saying,
is
but
it.
she's only studying the interaction at the apex with the apex, because this is
at different locations, you will have different parameters.
Yeah.
but what I'm saying is that assume the CME to be a very big sphere, the cylindrical can be assumed only at the top, right?
No, not even top. If the cylinder is like, the cylinder can be assumed here also, the cut portion. You cut the whole structure in short.
So how do you decide this orientation then?
Oh, that we get from the GCS model.
So you are using these.
Yeah.
Okay.
All the orientation parameter we get. So yeah, you can see here, this is a very good prediction of the thing, and as well as this dash line, which is which I put here. So that is the observed start and end point, but the red line, it does not follow the dash line because it is just completely from the model. So it very well matches with the front and end boundaries. So yeah, the next thing is, it is good that we got this kind of model, this kind of prediction algorithm, which can give you like within I will say 15 minutes of the data. Or once we get the data of the sun, we need 15 minutes to get this result. But this is not good for when the CV evolutionary impact is very high. Because this, we did many event analysis, and out of them, we got 2 events like this. So you can see it is very bad. This does not follow at all. So this is because of the structural asymmetry. So what happened here, the back of the CV, there was a high-speed stream, and it squeezed the CV as in a way that it was not at all similarly expanded, and our model failed. And then another event we got, that is this kind of event. So this, what happened for this event, that the event was very near to the heliospheric current sheet, and you can see here the event. This is the cylinder's axis. So this farm line, and this is very near to the heliospheric current sheet, and this which is shown by the black deep line. So this is the Carrington map. Means once you open the sun in the 2D map, you will see the structure like this at 2.5 solar radian. And then you can see the dotted line. So this was the previous, once the CME erupted, the orientation of the CME axis was this. And once it propagated to the interplanetary medium, its axis rotated and it becomes like this. So this thing we could not capture through our analysis.
So this rotation happens where?
In the interplanetary medium. So not after 10 hours. So we could not capture it by our own.
So anyway, you are giving the input parameters at 10
I got
hours.
good.
Yeah, additional.
Yeah. So yeah, so our model failed in doing that. Therefore, it is important to get semi-evolutionary impact in the interplanetary media. So what? So just a bit a thing I didn't say about semi-evolution. And then the way of CMEs and their interplanetary CMEs are rotated, reconfigured, deformed, deflected, and decelerated and eroded during their journey through the solar wind. So that is called the CME evolution. So deflection, it is called that when the CME erupts from the solar surface, if it does not go to the radial direction, if it just if it changes its propagation direction due to the magnetic energy minimum or maximum. So you can see here, this is a point which is going not radially outward, it is going this side, because there exists magnetic energy minimum region. So this kind of thing is responsible for the deflection. And then the rotation, the conversion of twist into right in a unstable region can cause this kind of
Is this Euphoria?
this one is not.
No, of course.
This one?
No, these are simple.
Yeah.
What, which model? Anyway.
But you can use Pluto to separate. But my question here is that, okay, we understand that CME has this deflection and rotation, but all these usually happens in the inner coronal.
Very near to the
But
sun,
then
yeah.
you are giving the parameters starting from 10 R now.
10 or not, yeah.
Yeah. So what I'm saying is, if all these things are happening in inner corona, you are already taken care of, right?
Few, yeah.
So the point is that if it is happening at
In the interplanetary.
in the interplanetary medium, then probably we need even more some new mechanisms how it is happening.
So yeah, that is happening now with PSP as well. So they can give us the information with the data. So I'll show in the next slide that here. So first, another evolution process, acceleration, deceleration. So that happens due to the aerodynamic drag. So you can see here the high speed streaming can be lower speed in interplanetary medium and then other way around. And then the next is the deformation. So due to interaction with the different solar wind speed, the shape of the CME can change. So very recent study by Braga et al. So they showed that they used the PSP observation and they showed that this is the stereo observation, so whole scores and the PSP's observation. So till 17 RS, till 15 RS, I would say, the structure of the CME was very uniform and it was not at all distorted at all. But when it reached to the 17 RS to 32 RS, so it had a serious deformation here. And this happened due to, they figured it out that this, they used the simulation from the predictive science simulation for him. And they found that there exists a high-speed stream, and that was responsible for its pancaking structure.
Similar results. I mean, I remember a long time back I attended a conference where Craig Forrest showed the similar results with heliospheric imager of the stereo.
That was.
He said that from the concave shape, the CMEs become from the convex shape, the CME become concave shape as it's moved through the heliosphere. Long time back, I think 2014 or 15, he was showing these results. So just wondering whether, I mean, the similar type of results are seen here. And then he said that it is because of the ram pressure of the ambient medium, because you continue to pile up the plasma as the CME propagate outward. And then at some point of time, the ram pressure of the medium, which is ahead of it, is actually started pushing back towards it. And that's why the convex become concave.
Yeah.
So just wondering that, I mean, these doctors are also claiming the same thing, but it was already observed from I think there's a paper by Craig for a long time back in 2014. Yeah, I think this is a recent one, but they have also done it.
So you said high speed ships. What is the latitude? I mean, it's pretty equatorial looks like.
Yeah, it was. Yeah. Here. And there was a coronal hole.
They could be coronal holes, but there is no.
Very near to the equator, and it was during the lower minimum. Okay, and finally, that is the CME evolution by erosion. So sometimes the CME is in front of the flux rope, and after the flux rope, we see this extended region, which is called as rear region and front region, and these are resulted due to the CME erosion. So this is a picture to show you how the erosion happens. So this is the interplanetary field lines. So these lines are interplanetary field lines, and which can be draped about the CME structure, and then they can reconnect here, and they can peel out the outermost layer, and thus this field structure, so they can accumulate in front or at the back of the CME, and then they can create this kind of region. And via this evolutionary process, the CME decreases its size as well as it loses its intrinsic magnetic properties, and these kind of things we have studied before. So I am not going on those things right now. So now okay, now as we know, we have a solar probe along with us, and that can goes very close to the sun, that is around 0.08 AU. And it had the science objectives like solar corona and solar wind heating, and then particle acceleration, structure and dynamics of solar wind. Mostly they were focused on the solar wind's properties and mechanism, the acceleration, or how the acceleration occurs. But now we have seen that using the Parker solar probes observation, we could very nicely do the analysis of the large scale structure also. So right now the solar probe's location is like this. So the radius orbit right now it has, So you can see it is very near to the sun. So, so we can get very nice result of early evolution of CME when it is launched in the interplanetary medium. And along with this, we have another spacecraft mission, that is NASA's and ESA's joint venture solar orbiter mission. So this will also go till 0.284 near to the sun, 0.24 AU, very near to the sun, but not that much near like PSP. But the special thing is it can go out of ecliptic plane, and that is like more than 30 dB it can go. It also has the scientific objective of the PSP, and additionally that is the sun's polar magnetic field analysis. So this also, fortunately, we also use this to get our evolution of the CME, the interplanetary medium. So the orbital structure I just gave here to give a brief view about the orbital structure, and we will be lucky after 2026 when the expected start of extended mission will happen. We expect the extended mission will start, and then we will get the out of ecliptic observation, and that will be useful for our analysis. So how do these spacecraft help in analyzing CME evolution? So first, probing the CME evolution very near to the sun, and which happens here. So as I said, that CME erosion happens in the interplanetary medium, starts in the interplanetary medium, but its impact can be observed at 1 degree. As we did not have interplanetary observation much, so that's why we could not see the draping. Previously, we could not see the draping of the magnetic field lines of the CME. But once the PSP came, or solar orbiter came, I use this here PSP, so that's why I'm saying PSP came. So it was around 0.5 AU when we did observe the draping of the CME. So the structure was like, so we saw, actually this was a stealthy CME. It did not have a good observation, characteristic observation, the signature on the sun, but it was a very good 3%
So
structure.
why you call this stealthy? I think
Yeah,
it's
because
called
it did not have any, you can see the,
Yeah, but it was named as stealth CME, STEL.
It is.
Why?
I mean, it's a stealth CME, but stealthy in nature.
Okay.
So,
Yeah,
healthy.
yeah, kind of.
Healthy.
So yeah, and this CME is result in depletion region. Means through this criteria we could understand it's the stealthy CME. Also low coronal signature, you will not see anything, and location mostly follow the tilt of the heliospheric current sheet. Here, so it is just a view of the CME's initiation. So it did not, it was not at all related to any active region. You can see this is the Carrington map of the sun, and there were no active region in surrounding the CME's location. These were there were back-to-back 3 CMEs, and the CME2 was mainly the stealth CME, and CME0 and CME1 was a very faint CME which occurred before the actual CME which we are studying. So, so actually it was related to the multi-flux arcade. You can see here 3 flux arcades were there. This is the PFSS extrapolation of the magnetic field, and we.
So this one very looked like a quadrupole region with a X point.
This one here was a null point. Yeah.
There was a null point.
Yeah. And this null point actually caused the eruption.
Yeah, I know, because I think this is something that Nitin is simulates, right? It is exactly the same. So he's also doing something like this. So it's interesting that you could get this type of configuration. This is using extrapolation, right? Okay.
So
And-
it's also
So
possible that
it's a breakout.
it's a thing has gone back, backside. So did you look at the earlier connected map or something? Because there's some signature of the magnetic field.
Okay, from the back it is coming
Yeah.
front, you are saying?
No, I mean, it has gone already to the back. Not come, I mean, you probably have a full rotation of the.
Yeah, I have the full rotation, but still here, I mean, the previous, it's like here. So what we saw here, first, there was a flare reconnection at the top here, which showed us the coronal brightening here, which occurs the CME0, and it was a very narrow CME, and not even CME, can be said as ejecta. We are saying it's CME as it's depending on the 40 degree, less than 40 degree of. So yeah, so this was the CME, and then there was CME2. Here I can show. there was a CME2, CME1 actually, CME0 was this, this kind of just this jet, and then there was CME2, and CME2 had a big flux of structure, but it was mostly on the ecliptic like this. It could not be observed well, that's why we could not see much on there, that. And then the CME2, which had a good structure, which actually observed, came with its structure till 0.5, not the other one. So here, we tracked the front edge of the CV, and we got like this. The CV0 was very high speed because it was kind of a jet, and yeah, and then the CV1 and CV2, and this CV2 actually caused due to it occurred due to the breakout reconnection, and which is occurring at the top coronal height, and that's why we could not get any signature on the low coronal. And this is the observation by the solar globe, where you can see the blue block, which is the actually CV flux flow. And I showed here many dotted dashed line. I will say here, so I don't have to go through these big things, and it just concentrate on the image. So here this shaded this region and this region, they are actually the heliospheric current sheet crossing, and we can get to know about this because there are several characteristics which can be used to classify this region. And heliospheric current sheet means there should be the reconnection region, and where the sudden jump of plasma beta should occur and sudden jump of density, and what percentage of jump occurs, so that also we use here to identify the crossing of heliospheric current sheet at the front and at the back. And then here we drew here one schematic which is following our observation, and which you can see here the blue line, so that is the heliospheric current plasma sheet. So heliospheric plasma is surrounding the heliospheric current sheet region. That's why this is a thick region. And then the field lines orientation, if you concentrate more on the orientation, you can see that they are very nicely capable of having the magnetic reconnection at the front of the CV. And then finally, this cyan color line you can see, so they are piling up they are being piled up at the rear of the CV, and which is related to this region. So enhancement of magnetic field intensity definitely is small region. So yeah, so and this here was the PSP and the observation here. So first time we showed here the observation of the CV of the field line breaking about the CV, and it was possible due to the PSP because PSP went till that and it gave us information. So the CV eruption mechanism was a part of multi-stage sequential eruption. So for this work, we collaborated with Ben Lynch, and he is very expert in this thing, the sequential syntactic eruption. So, and he helped us to analyze the origin of the CME, and then I specifically did the interplanetary medium analysis.
Probably elaborate what is sympathetic.
Yeah, so what happens here? Yeah. So what happens, I said here, there are 3 consecutive CMEs. So CME0 occurred, and CME0 opened the, yeah, so once the CME0 occurred, so that was from here. So this opened the overlying magnetic field region, and for a brief period of time, and once they just opened this thing, then continuously this arcade was going up due to the excess magnetic energy, and the null point was just sitting here, and due to this null point, this arcade's magnetic field lines came very near to each other, and magnetic reconnection occurred in this region. And once this magnetic reconnection occurred, it opened the path here, and this caused the other eruption. So that's why CME0 caused the CME1, CME1 caused CME2. So that's why the sympathetically it erupted one after another. And
so the question that I have here is that you see the flux of signatures there in C2. So was there a filament of prominence associated here? If not, then where is the flux of forming?
No, there were no filament prominence.
So then the question here is that where is the flux of forming?
The flux of formed even after this core ones.
So how do we? I mean, how do we know about this? That's what. Because this is an open question. I mean, where exactly the flux ropes are forming?
Yeah.
Because we do not see many flux ropes here, but then again in C2 suddenly you see these rotating.
Only means there are no observation of what you are saying. Only we get to know this depending on the physics of this arcade structure, how they evolve and how they interact with each other, and how one eruption.
I mean,
Is there
these
any
helical-
models which is able to, I mean, Nitin,
No,
Digna
no,
has
we are getting plus in the simulation.
no,
That's why I'm asking where you are getting here, so that we can match the heights. And he's getting a different heights.
Have you looked at this particular event?
Then the flux from.
तो मैं वही बोल रहा था, sympathetic what comes because of that,
Yes.
that the overlying arcade, when it is released, you have an easy channel to escape.
But
But then how do you form it?
form this helical field, that is also important.
So there has to be some motion.
That is the problem with our model, our is only 2D model. So it will only show the circular
Yeah, yeah.
structure, not the.
No, the field lines which sitting here, so those structure mainly erupt. I mean.
Yeah, but
there
there has
is
to
a-
be some rotation and some helicity,
Because
which
that,
has to be injected.
Yeah.
The point is, if
Yeah,
it's
yeah.
just simple field lines, the flux loop will not form. So
Yeah.
there has to be some helicity from somewhere.
yeah, so first breakout reconnection occurs, which does not need any helical field lines. Then the breakout reconnection causes this flare reconnection. And this flare reconnection is mainly happening due to the flux.
We also see this happening in our simulation.
Yeah, yeah.
After breakout CME, we see the state of area connection, which also causes.
Exactly, yeah.
So time scale थोड़ा match करना.
Yeah.
This-
I was
this
about to
particular
ask, what
event-
is the time difference between
Yeah.
these two CME?
Uh-huh.
These-
Yes, you can get to this.
So this the event का देखना.
Yes.
20 का.
So here is a QR code, you can scan it, put in the paper. So we got 20% of the erosion occurred at 0.5 AU and the erosion started occurring at 0.35 AU. So it is in the interplanetary medium. Okay, next is the enabling, how much time? Oh, no. So enable, this PSP and solar orbiter, it enables the multi-point observation to study the CV of evolution and how this multi-point observation helps us in evolution. I will show you. And this is a very recent work which we have written and just need to submit it, and it's just an overview. So what happened here? So the CME, there were multiple CME back to back, but main interesting CME was this one. So the three spacecraft was here, so stereo and then solar orbiter and then L1, like S or V. These spacecraft were there and they all observed the CME at the interplanetary medium. And the energy transfer, as I showed you, so so this is very peculiar thing happened. So at stereo, when we calculated the energy transfer, and as L0 was constant, so we took L0 also for stereo as 6RE, which is not true, but we can take that because it's a constant. So at stereo, we got almost a constant value of the epsilon parameter. But in the L1, we got very high value. It was like 25 times higher. For the same CME, it occurred two type of things. So two type of geoeffectiveness. If the art was there at the stereo, then geoeffectiveness was not at all geoeffective. But at L1, it was geoeffective. So how this is happening? It's just so this event is very important. I mean, many studies have been done on this event because this event was responsible for the SpaceX satellites. Okay, so the event, first of all, I need to mention here, the event was launched in structured heliosphere. What is structured heliosphere? That is, if there is multiple large-scale structures, like you can see heliospheric current sheet, then high-speed stream, then SIR, all are together along with the CMEs. All are propagating in their own way along with the CME, then we will say that is a structured heliosphere. And the CME was fortunately launched in the structured heliosphere. So this is the observation in here, that is location 1, that is the stereo, the point here. So you can see here the shock was there, then sheet, then CV flux, so then SIR. So SIR is the stream interaction region which occurs when the high speed stream tries to overtake the CME structure. Then you will see the pressure is enhancing, and then the TP, the temperature will enhance, and this kind of signature you will see in the SIR region. This is just, I could not figure, I mean, put it in a single panel. That's why I broke the panel into way. And here, this blue lines is showing you the energetic particle during this region. So shock and steep region, you should expect energetic like particle energy enhances because it gets the shock. And then the last panel is the epsilon. So as epsilon depends on the B and B, also the theta angle. So and BN, like which is a BZ, which was almost this blue line, and it was almost like positive throughout the interval, and it did not cause any geoeffective nature. Solar orbiter again it cracked, so it did not give us any magnetic field orientation based on the energetic particle information. We could figure it out. There was shock, sheath, And also there was flux when the energetic particle will be very, it is energetic particle means if they are not related to their eruption on the sun, this particle energy enhancement is occurring in the interplanetary media, which is very low in the flux. Should. And then next is the L1 observation. There also we saw the similar kind of thing which we saw in stereo, but we saw additionally two CMEs, CME2 and CME3, and they marched in the planetary medium. In between, in between the CME1 and SIR, we saw this region. So this is a new region which stereo did not saw. And then this is the flux of fitting which we did in the stereo as well as in the wind observation. And the stereo, we got the flux of orientation like this. And the wind, we got flux of orientation like this, which is together creating a V kind of structure. So V kind of structure means like this. So if you assume that the fluxome is the local structure of the fluxome is here and this is L1 and this is stereo, and as we did not get the solo observation of magnetic field, we could not feed that here, and it is giving us kind of this structure. So somewhere it is bending here in the solo observation. And then here is a why this kind of thing is happening. We are going behind the reason. And we found that the CME at the location, at the source location, it had two structure. So here, this is a stereo observation, this is a last observation. So you can see here this structure and these two structure, which is here hiding inside this thing.
So there we are two CMEs.
No, I'll come here. So what happens here? So it is this is fitted at around 8 to 10 RS, this GCS model. So we fitted the event with two separate DCS models, and which was very similar to what we got in the interplanetary media, like the structure. And also we did a fitting of the fitting result we put in the model, which predict the series speed as well as its arrival time at the spacecraft. And this S1 and S2 is based on the S1 is simulation assuming CV1 as a single structure, and S2 when we assume the CV1 as a double structure, which I fitted the result I just showed. So here you can see the result. So this is the stereo result. This is the solar orbiter. This is the wind result. So you can see the red line. So the red line is when we assume the CV, the two structure CV. And you can see here for the S2, we got the difference between the arrival, the modeled arrival and the simulated and observed arrival time is very small. So it means that what we did, we fit the CV with two structure, so that actually gives us a better result in even in modeling the CV.
No, but so I just get it. When you say that there are two structure,
Yeah.
so
I'm
how
coming
did
out there.
yeah.
So yeah, so this is the now how these two structure is happening. So so what we did the active, we saw the active region. So this is the stereo's viewpoint, which was from here. So we saw here two active regions were very close to each other. Here also it is the Earth's viewpoint and it's SOHO's viewpoint. Sorry, SOHO's viewpoint. And then this active region 1 and active region 2. So this active region 2 was very strong, and even one impulse flare also occurred during the CV eruption. And you can see the red line is the PIL, but active region 1 was not at all strong. So initially we were thinking there are two CME happening from active region 2 and active region 1, but active region 1 was very nominal magnetic field characteristics it had. And but active region 2 also showed us very brightening during the flare. So there exists one. I showed already that they were the high-speed stream was behind the structure, and this high-speed stream was originating from the coronal hole, and the coronal hole was very near to this active region 1, and the CME occurred around this region. So next I will show you the red line you are seeing. So this is the coronal hole coronal dimming region. So this coronal dimming region represents us the plasma evacuation from the solar disk, solar corona, when this CME occurred. So we during the eruption of the CME, we stacked the data and got this structure as the plasma evacuated region, and then this involved this active region 1 also. So then we were surprised that how this can be happened, because active region 1 was not at all very active. So that's why we discussed and we figured it out that this may happen that the reconnection between the field lines of two active region at higher corona, which is breakout reconnection, triggered the explosive flare reconnection at active region 2. So, which is this. And also caused a one flare and along with the flux of one eruption. And once the eruption occurred, so the CME flux was like this as, so it was like this. And then the part here, so that part got deflected from the coronal high stream from the coronal, so the higher magnetic region. So that's why only this portion got kind of restructured and go up. And that's why.
Sorry, maybe I'm not. So it will be deflected, that's fine. But still, why do you see two different structures?
Because that already deflected and it.
So you are saying that from the CME as a whole, only a part is deflected.
Only a part is.
Other part is moving like that.
Yeah. So.
But then that is, okay, it could be very interesting phenomena. But I think if you consider it to be a single flux flow, it's very hard to get this flux flow only one part of flux flow get stretched to one direction, other part of flux flow to be moved in another direction. So there's a lot of magnetic field, and plasma beta, as you said, is very less. That means it is magnetically dominated. So how come the coronal hole stream are able to deform the CME in such a manner that you see these structures? And this is something that probably is for good. We can investigate.
So you're still claiming that it is the same structure because of the one part being deflected, you have got deformed. Now, what his question is, of course, it can get deformed locally, but then because of the high tension, the tension will dominate as it propagates out.
It's a very strong magnetic.
Because the reflection region is gone.
Yeah,
The reflection region was,
and you know that too very near to the sun. So there was a paper by Prasad Subramanian where he has shown that very near to the sun, CME move like a solid sphere, I mean, because its magnetic field is so high initially, and when it expands, of course, magnetic field will go down, and that's why you should expect deformation in the higher corona. Fine.
Yeah.
But here, I don't know. I mean,
you are.
I understand that it is matching with your arrival time and all those things.
So what happened? The coronal hole was very strong also. So the coronal hole.
The stream is extending to very high distances.
Then it might happen because.
I mean,
we were also very confused how this can happen, right? Means it's a very weird thing. So then we sit and analyze how the magnetic field configuration can occur to cause this kind of bend.
Probably need to someone need to do some sort of MHD simulation because there one can really understand these forces.
Yeah. That is our plan next. That we will do that. We will involve Judy Culpet and those people to do this analysis. Yeah. So also here the dash line shows the coronal wave front, so that is a kind of a proxy of the CME's leading edge when it propagates to the just early propagation. And we saw that had kind of this kind of structure, and the red dash line you see. So this is what L1 observed, and this is also what the active region's PIL implication was. So that's why the summary is the overall complex structure heliosphere contain multiple CMEs, then shock, then multiple time heliospheric current sheet crossing, SIR, HSS, all interplay among them and made the space weather geometric only at L1, not in other area. And the presence of nearby coronal holes sourcing the HSS locally deflected the flux of 1 and transformed the part of flux of 1 and transformed its geometric structure. And the multi-viewpoint analysis, of course, the multi-viewpoint analysis helped here and made it possible the comprehensive understanding of the whole structure. So in my conclusion, I will say that as we have right now many spacecraft in the heliospheric region, and we have many scope of doing analysis of CME or this kind of large-scale structure in the interplanetary medium, along with the origin and along with this observation at 1 AU. So the fleet of spacecraft is helping in uncovering more unknown facts of sun and heliosphere. So I'll encourage the new people that to concentrate on the interplanetary medium also, how they evolve, how the things are happening, and of course using the new spacecraft which are now giving us very good result. So here I will show you, so you can scan this QR code, and this is a website which I made for the new people, the newcomers in our field. So here I put the study materials, several good papers of this PhD thesis are there, even biopsy thesis is also there, and all thesis. So these are all new studies. Yeah. And then the books which are openly available, you can go there, and it will be, I think it will be helpful to the new people. And also the database, there are large section of database from where all the data can be, in my knowledge, can be accumulated. So you can find it there. So with that, I will.
Okay, thank you for the very nice talk. So now we have time for questions.
The necessary that all the CME are related to your activity.
No, not at all. No,
You are not, because you are doing the activity in CME, right?
no, the CV which I showed by purposeful observation, so that is not activity.
No.
Yeah, so that is formed at the higher coronal.
And there is a CME, and do you see the, say, for example, in case of the ghost light went on, do you see the dimming and all?
For that kind of CV, which is no. I mean, dimming not on the solar corona. I can see dimming, so I showed you the dimming was observed. Yeah, see, the dimming is a nature of the this kind of CV, but it should be at here. I mean, in the coronal. I mean, photograph using photograph. Not on the.
He's asking that you see the X-ray.
Similar to the.
What?
X-ray like that.
Oh, no. I mean, I did not try.
For example, goes in the soft X-ray, it is accumulated by the CME and also it has to be.
Can be, I mean, I could have.
Yeah, but it's at the end of the day integrated flux, huh? So these are only in the local. So these are actually local effects. The depletion is only local. So if you sum it over everywhere, that depletion is very marginal.
In that way, maybe there is not that much of the significant, but in case of the stars, we will see the dimming.
Yeah. So the stars mostly the
They're very-
structures are much larger.
Yeah, much highly active.
Yeah.
So here, I think most of the things have been seen in UV lights.
Yeah.
So UV, they have seen the dimming at a catalog of the.
Even the UV waves and all that can be
these are
behind.
the images.
There is a recent paper in Nature by last year, that coronal dimming.
Yes.
But they have done also this, whose light comes and
Ah,
it just show that
yeah.
dimming and all, that's what I'm asking.
But those are much bigger even. Yeah. So this is actually
Okay.
called still it doesn't have any signature in the surface at all. So you're not able to identify the source. Kahan se aa raha hai. It's so weak. But at the same time, there is a scene in the coronagraph. So that means it has formed somewhere in between.
So as a input, you near the sun at 15 solar radius. So what parameter exactly you give as the input? I mean, the parameter gets from get from the
TCS, I mean,
GCS or
TCS and then speed. Speed
kinematics. You
also.
also calculate the kinematics. You get it from catalog zero or something.
What?
So he is saying that the parameters that like the velocity and other things that you are giving in your model. So that parameters you have taken from a catalog or you
Oh,
computed it using GCS?
But is it just a plane of the sky?
No, GCS.
Or you have
TCS
TCS?
speed.
Oh, yeah, the 3D. The full velocity also is from TCS.
Yeah.
The beginning you mentioned the relation between the speed angle of the ICMs, the picture types. How it's related?
Twisted magnetic field lines.
There is was one equation. Static type.
So the twisted field lines are inside the magnetic field, and then if the spacecraft goes to this, then you can get to the twist in the magnetic field lines in terms of the time evolution of the field.
And the event that we talk about the Starlink event. So that was geo-effective that you calculated at the near surface. It is compared to that one. So what exactly changes you expect? Is it a rotation only or you are using at the different part?
Yeah.
So what exactly you mean?
The rotation only, the B field rotation. So once the flux slope was at L1, the flux slope axis was like this. And the handedness of the flux slope was right-handed, so it was like this. And then at stereo, it was like this. So you can see the BZ of this kind of structure is southward here, but the BZ is not at all southward here. So that's what the epsilon is. That's why.
Okay, so I have one question that you showed the performance of your empirical model with the real observation. You said that whenever there is a high speed streams and other, or let's say current sheet, then the performance is not so good. So, so if you, I mean, what is the total, I mean, how good is that model? I mean, how many events have you tested this model on?
Right now I did 12 events, and out of them 2 events like this I got. But now what we are doing, we are giving input to the model in the planetary media using the PSP and solar orbiter. So they are helping us. So if say the B field direction changes or something happens, then from that observation in the in between 1 and 2, we get to improvise our model at that region. As this model takes very few times to get the result, so we just put the input there and we'll get the output at what anyhow. This is our plan. More observation if it comes, then yeah.
Okay, any other question? That density greater than -10 nano.
Yeah, yes, yeah.
Why there is minus?
Oh, that is the BZ value. So BZ should be negative. Then only we can interact. BZ is the magnetic field.
Negative is the
You
direction.
see, magnetic field direction. Yeah.
Negative is the direction.
Magnetic field is a vector quantity. So it should have 3 parameter axes: Bx, By, Bc. So the Bx is along the Sanat line. By is perpendicular to the Sanat line in ecliptic plane. But Bc is perpendicular to the ecliptic plane as well as perpendicular to the Sanat. Easy. So once if I'm the earth and if my magnetic field is towards north and the BZ is towards south, then the reconnection occurs. And that's why we need negative for getting.
Unless the sun flips.
Yes. And also earth.
Sorry, not sun.
Yeah.
जब sun में होता है कुछ नहीं होता है. I meant earth flips.
Yeah.
Sun में कुछ नहीं होता है.
Okay, any other question? Okay, if not, then let us thank Sanchita again.
Yeah, Sanchita is around for 2 more hours today. If you want to interact, I think we're going up. He's staying in the first floor. Yeah. ये सब मूवी पेनड्राइव से चला.
No, she copied everything in the computer.
वो session off कर देना.